Hi everyone. Today we're going to be taking a look at an interesting physics problem where we will try to calculate the electric field at a certain distance from different charged objects. So for example, a point charge, an infinite wire, and an infinite plane. So we will start with the point charge, the infinitely small point charge. So from Coulomb's law, derived from Coulomb's law, we know that the electric field at a certain distance from a point charge has the formula E equals kq over the square root of the distance. So we'll call the distance r, because like we imagine at a radius r from the point charge, because the electric field like on the surface on a sphere with its center in the point charge, the electric field strength is the same. So knowing this formula, we will try to find the formula for the electric field strength at a distance from the infinite wire. So imagine we have this infinite wire that's uniformly charged with a charge density, let's call it lambda. So this is like a length charge density. So this will be dq over dl. And we want to measure the electric field at a distance r from a certain point, let's say B on the wire, and A is the point where we want to measure the electric field strength. So if we know that the wire is infinitely long, this point B is basically the center of the wire. Anywhere you choose this point B, it's going to be the center of the wire. So if we imagine a small portion of the wire, so this one highlighted in red, that has a length dl, so it's infinitely small, so it acts just like a point charge. Its electric field strength will be along the direction of that point to point A. So we'll have here, let's call it E. So this is the electric field strength from that small point of the wire. Now, there is, for any point we choose on one side of the wire, there is another point that's at the same distance from the point B, so it's symmetrical, and it will create another electric field, small like component of the electric field, along its direction to point A. So let's call this E prime. And notice one thing, these two electric fields are symmetrical. So their horizontal components will cancel out and only their vertical components will add up. And we can do this for any 2 points on the wire. So let's say we choose a point here. There will be a symmetrical point on this side that will create two symmetrical electric fields that will cancel their their horizontal components out. So if we want to add the electric field, like the contributions due to every point of the wire, we only need to add the vertical components because the horizontal ones will cancel out. So let's say this is the direction like AB, and this is an angle alpha. So we want to add each electric field strength due to each point, but only the cosine, only its vertical component. So let's call this distance r and this distance L. The electric field strength due to one point will have the formula, let's say dE equals k dq over the distance squared. So the distance squared will be L squared plus R squared. Okay, dq will have the formula lambda times dl, because lambda is the charge density, and we know it has a small length dl because we chose it to be like that. So dE will be k lambda dl over L squared plus R squared. Okay, now we want to add all of these components, and we want to double everything because we're doing it for half of the wire, but we have two halves. So E will be equal to double the integral, so 2 times the integral from 0 to infinity. Keep in mind we're integrating over L. Okay, so integral over dE cosine of alpha. Cosine of alpha. Now, cosine of alpha, we can express it from this triangle here The cosine of alpha will be, oh, sorry, no, this triangle here, because this angle is also alpha. So the cosine of alpha will be equal to r over r squared, sorry, the square root of r squared plus L squared. Okay, so our electric field will be 2 times the integral from 0 to infinity of dE, that will be k lambda dl over L squared plus r squared times r over the square root of r squared plus L squared. Okay, we can bring up front the constant, so that will be 2 times k times lambda times r times the integral from 0 to infinity of, and we'll have dl over the square root of r squared plus L squared, but to the third, because this term here is the square root squared, and this is just the square root. So it squared times itself will give the square root to the power of 3. Okay, I'm not going to go into detail right now as to how to solve this integral. I'll make a separate short video where I will explain how to solve this integral. I'll probably make it in short video format. But I'm just going to tell you for now that this integral has the solution, the square root of 1 over r squared over the square root of r squared. So this simplifies to 1 over r squared. Okay, so now our electric field will be E equals 2k lambda r times 1 over r squared, and the r cancels out, and we'll have 2k lambda over r. And this is a really interesting result, because before, for the first case where we had the point charge, the electric field drops off with the square root of the distance from the charge. But here, the electric field drops off only with the first power of the distance. So the electric field at a certain distance will be much more powerful than in the first case. Okay, now we can move on to the infinite uniformly charged plane. And I'll copy this drawing because it's easier. Okay. So this is our plane. And we want to measure the electric field strength at, let's say, keep the distance like r, keep the notation. So this is point A, this is point B on the plane, and this is the distance r. Okay, so how can we do this? Maybe do it in a simpler way and make use of what we calculated before. So we can think of this infinite plane of it being made up of very thin, infinitely long wires, just right next to each other, like small strips. And we can integrate the electric field just integrating the contribution from each of these wires. So if we choose, let's say we choose just one of these wires that, again, let's say is at a distance L. Okay, so keep in mind this is three-dimensional like that. Okay, and we want to integrate for 1/2 and then double everything because we have 2/2. So we have this first half and then the other half because everything is symmetrical, and we're gonna again only add the cosine of each of these electric fields. So let's say that this is our electric field, dE, and we want to multiply it by the cosine of alpha. Okay, so again, the cosine of alpha will be cosine of alpha equals 2. It's going to be r over the square root, again, r squared plus L squared. Okay, and we have the formula that dE, this time dE, because the charge on this wire is infinitely small because it's infinitely thin. So to calculate the charge density lambda, we will say that the charge on the wire can be calculated in two different ways. Lambda times L, where L is its length, but L is infinite. And the charge can also be calculated using the area of the wire. So this will be dl, because it's infinitely thin, times L. This is its area because it's a very thin rectangle, times sigma. L cancels out. So then we'll get lambda equals sigma dl. Okay, so we know dE has the formula 2k lambda over r, where r is the distance, but in this case it's not the same variable, so r is actually going to be the square root of r squared plus L squared, because that's the distance. This one is the distance from the wire. Okay, so now we will integrate the electric field strength. So actually we're going to say E equals to 2 times the integral, because it's like the 2 halves, from 0 to infinity of 2k lambda over the square root of r squared plus L squared times r over the square root of r squared plus L squared. Okay, and this is going to be, so we'll have E equals 2 times the integral from 0 to infinity of 2k lambda r over r squared plus L squared, because the square roots cancel out. So this will be equal to 4k lambda integral from 0 to infinity of r squared, just r over r squared plus L squared. So this is going to be equal to E equals 2 times the integral from 0 to infinity of 2k sigma dl, because sigma dl is actually lambda, r over r squared plus L squared, because the square roots cancel out. So this is going to be equal to 4k sigma r, yeah, that's correct, integral from 0 to infinity of dl over r squared plus L squared. So this is integrating over the distance L, so the distance of the wire from the projection, like the point projection of the point we're actually measuring at. So we're not going to calculate this integral now. Again, I'm probably going to make a short where I will explain how to calculate this integral, but I'll just tell you that this has the formula pi over 2r. So if we continue our calculation, this will be equal to 4k sigma r times pi over 2r. The r cancels out and we will have a 2 left. So we'll have 2k sigma pi. And we'll write k as 1 over 4 pi epsilon 0, and we'll get rid of the pi. So this is going to be equal to 2 sigma pi times 1 over 4 pi epsilon 0. And what we'll have left is sigma over 2 epsilon 0. So just look how beautiful and how simple the result is. So we've gone from a point charge where we know the formula for the electric field derived from Coulomb's law, and we calculated it for an infinite wire. We saw that it drops off with a radius, with a distance, with a radius basically, because the electric field will have the same strength on a cylinder. So imagine like a cylinder surrounding this wire. On the surface of the cylinder, the electric field strength will have the same value. And then we considered that the infinite plane is composed of infinite, like very thin wires, and we integrated the electric field for each of these wires and added them up, and we got the result sigma over 2 epsilon 0. Now this is really interesting because you may observe that this is independent of the distance r. So that means that we can be infinitely far away from this infinitely large plane, and the electric field strength will have the same value, and we can be infinitely close and nothing will change. So the electric field is constant. And this we're going to use when we will calculate the capacitance of a capacitor. We will use this knowledge basically to make our lives easier. Okay, I hope you enjoyed this video and I hope it was helpful. If you have any questions, just feel free to ask me in the comments below, and I'll see you next time.